Right, here we go. Not many days of new stuff left. Today is day 120. And we're talking derivatives and integrals of tan inverse today. So you need your own paper. There's no note sheet for today. Here is day 120. So again, this is derivatives and integrals of y equals tan inverse of x. Okay, before we get into tan inverse, let's do a quick review of sine inverse. I know it's been a couple days. So a few days ago, we did the derivative of sine inverse of stuff, I'll call it u, is equal to 1 over radical 1 minus u squared times the derivative of u. Again, that u, don't think of it like u sub. We really probably should use a different letter. That's just stuff, so derivative of stuff. So that is the derivative of sine inverse. And then we also did the integrals, not the integral of sine inverse, but the integrals involving sine inverse. And that's when they had 1 over radical 1 minus something squared du. And when you see that, obviously just going backwards from the derivative, you know it's the same as sine inverse of u plus c. There you go. So let's do some practice with that before I show you what tan inverse looks like, because it's similar. If I just said to evaluate, first one, we'll say find y prime if y equals sine inverse of radical 1 minus x squared, or just 1 minus x, radical 1 minus x. Okay, so it's a derivative example, and I've got stuff in the center here. So we know that y prime, because it's sine inverse, it's going to be 1 over the square root of 1 minus, now this is the stuff, it's radical 1 minus x squared times the derivative of that stuff. When I'm taking the derivative of the stuff, remember you want to think of this as 1 minus x to the 1/2 power. So the derivative would be 1/2 times 1 minus x to the negative 1/2, right? Don't forget to subtract 1 from the exponent, times the derivative of that, which would be negative 1. Okay, so when all is said and done, I'm going to have a negative 1 on top. And the bottom, we've got radical 1 minus, now what's this become? If I square that, that would just be 1 minus x. So 1 minus, in parentheses, 1 minus x, because we're going to have to distribute that negative through. This 2 is on the bottom, so I'm going to throw that out front over here. And this negative exponent really means that there's another radical on the bottom. That's radical 1 minus x. Okay, now what's this turn into? Well, if you look at it, this is 1, if I distribute this, this is plus a negative 1 plus x. So that whole thing under here is just x. So I could say my final answer is negative 1 on top over 2. And since these are both radicals, x times 1 minus x, I could write it underneath one radical if I wanted to. Just again, multiple choice is going to be a big part of this AP, so make sure you're understanding how to rewrite situations like that. So they could even say x minus x squared. Any of those would be acceptable answers. Okay? All right. Number 2. 2 is an integral. I'm going to do an integral with bounds from negative 1/2 to positive 1/2. of 3 dx all over radical 1 minus x squared. Now, if I wanted to, could I make this 2 times the integral from 0 to 1/2 of this? No, be careful. That was a trick we used a lot in the volumes unit. You can do that, but only if the integral of the thing you're taking is symmetric on the y-axis, and I doubt this is. Okay, so what you're supposed to see by this is it's almost exactly the same as that integral. I see a 1 minus something squared. I don't even need u sub. What can I do with that 3? That can come out front, right? So this is going to be 3 times the integral from negative 1/2 to 1/2 of 1 over radical 1 minus x squared dx, which is just going to be 3 times sine inverse of x evaluated from negative 1/2 to 1/2. There's no plus c there or anything like that because we got bounds. I'm going to leave this 3 out front. We'll deal with that at the end. I think that'll be easier. Okay, so now this is going to be 3 times sine inverse of 1/2 minus sine inverse of negative 1/2. We're going to have to draw pictures. So sine doesn't exist. Sine inverse doesn't exist on the left side. Sine can be positive in the first quadrant. Opposite is 1, hypotenuse is 2. Missing is radical 3, which makes that a 30-degree angle. So this is going to be 3 times 30 degrees. What's that? Pi over 6 minus the same thing over here. Sine doesn't exist on the left. Since this is a negative, sine can be negative down here. Opposite hypotenuse, same triangle, just different quadrant. So what would we say that answer is? Right, negative pi over 6. So add pi over 6 plus pi over 6, you have 3 times 2 pi over 6, which is 6 pi over 6, because the 3 just goes to the top, remember? So your answer is pi. Okay. Let's just do one more, and then we'll get into this new stuff. So the other type that I showed you the last time we did notes were ones like this. The integral, no bounds, of 1 over radical 36 minus 25x squared dx. Okay, now again, these are a little bit harder to recognize. It's the radical on the bottom with a minus and some valid term that's squared over here. That's good news. Bad news is we need a 1 here. Anyone remember what I did? We kind of did a GCF trick because that's like dividing. So I took the integral of 1 over radical. We took a 36 out underneath the radical, and that left us with 1 minus 25x squared over 36. Like that. And then what would come out front? Remember, this is really 1/6 radical 36. So I could bring a 1/6 out front times the integral of 1 over radical 1 minus 25x squared over 36 dx. And so we did a weird kind of u sub. What did I let u equal? It's kind of a trick question. I didn't let u equal anything initially. I let u squared equal this piece over here. Let u squared equal 25x squared over 36. Because remember, I wanted to end up with u squared in that bottom right spot. So let's just make that u squared. So that what does that mean for u? It means that u would be 5x over 6, which isn't going to be a problem when I take the derivative. If I do du over dx, what do I get? 5/6. And my leftover piece is just this dx. That's the only piece I can't deal with. So if I get dx on this side, multiply this by 6/5, so 6/5 du equals dx. Okay, so now there's going to be a 6/5 out front times that 1/6 that was already there times the integral of 1 over radical 1 minus u squared du. So now I have 1/5 times sine inverse of u plus c. And then just remember you're plugging the right thing in for u. We got to plug in this 5/6 x. So it's 1/5 times sine inverse of 5x over 6 plus c. And there you have it. Okay, so that's some quick review for you. I'm going to flip the page, and now we'll get into tan inverse. So now, tan inverse of x. I'm going to derive it similarly to how I derived the sine inverse one. For us now, the original function is y equals tan x. So the inverse function, I could write it as tan inverse, but that should be equivalent to x equals tan of y. Inverse just means switch x and y, remember. So from this step, I'm going to take the derivative implicitly. So what's the derivative of x with respect to x? 1. What's the derivative of tangent of y with respect to x? The derivative of tangent is secant squared. Okay, so it's going to be secant squared y times dy dx. That's that implicit part. I want to solve for dy dx. So 1 over secant squared of y equals dy dx. And there's your derivative. Now the problem is, again, if I'm wanting the tan inverse of x, I don't want my derivative to be in terms of y. It's just not good. So do a little trig sub. What do you know? What formula do you know that has secant squared into it? Well, 1 tanning is secret. I guess I could say y here, because that's really what I'm using. So secant squared y is equal to 1 plus tangent squared y. So I could rewrite this as dy dx equals 1 over 1 plus tangent squared y. Okay, and then remember, what's tangent of y equal to? We'll look back at this step. Tangent of y is just x. So tan squared y is going to be x squared. Okay, and there you have it. The derivative of, oops, I don't want that y there, sorry. The derivative of tan inverse of x is equal to 1 over 1 plus x squared. And as usual, we can extend that with chain rule and say the derivative of tan inverse of whatever is equal to 1 over 1 plus whatever squared times the derivative of whatever, or stuff, if you will. Okay, so similar. The nice thing about this is I don't have a square root. When I did this substitution with the sine inverse, I used sing the chorus once, and to get sine alone, I had to take the square root. But this already had a squared in it, so that's why there's no square root in my answer. There's still a 1 in this spot. It's still a fraction. There's still a 1 in this spot. Instead of a minus like there was with sine, it's a plus, and there's still something squared. So two big differences is there's no radical, and it's minus instead of a, or a plus instead of a minus. Okay, let's do some derivative practice. So for all of these, we're going to find y prime. Start easy with y equals tan inverse of 3x. Okay, the derivative is going to be 1 over 1 plus the stuff, so 3x, all that squared, times the derivative of stuff, which is 3, which means my final answer is going to look like 3 over 1 plus 9x squared. Make sure you square both pieces of that, 3x. Good so far? Of course it is. Number 2. Y equals, not much harder, tan inverse of 5x cubed. So I see tan inverse, so I know my derivative is going to be 1 over 1 plus something squared. In this case, that something is 5x cubed times the derivative of the stuff. What would that be? 15x squared. So my answer is 15x squared all over 1 plus, square that whole piece, you're going to get 25x to the 6th. That's it. Okay. How about y equals tan inverse of e to the x? Remember the derivative of e to the x? It's going to be y prime equals 1 over 1 plus the stuff e to the x squared times the derivative of e to the x. The derivative of e to the x is e to the x. So your answer would come out being e to the x over 1 plus, what would this be? E to the 2x. Okay, I think you're probably getting the hang of it. We'll just do one final one. Find me the derivative of y equals arctan of 2 to the x. Okay, now obviously when you see arctan, don't get confused. You know that's the same as y equals tan inverse of 2 to the x. I just wanted to write arctan because sometimes you'll see that. It means the exact same thing, just different notation. So no difference. The derivative is going to be y prime equals 1 over 1 plus what? 2 to the x squared times the derivative of 2 to the x. And again, that's one that I don't think of too much. Think of it like an exponential e to the x. It's going to stay the same, 2 to the x. Since it's not e, what else do we have? Times ln of 2, right? Okay, so y prime, my answer would be 2 to the x times ln of 2 all over 1 plus 2 to the 2x. If they wanted to be annoying, they could always say 2 to the x times ln of 2 all over 1 plus 4 to the x. Just realize that that's the same. I could do 2 squared, 4, and then leave it to the x power. Okay. Questions on derivatives? Don't see any hands, so I'm going to go on to my last part of today, which is integrals. Make a new page. And now, integrals. So integrals, again, like with sine inverse, it's not integral of tan inverse, it's integrals involving tan inverse. So when you see the integral of 1 over 1 plus x squared dx, that's going to be equal to tan inverse of x plus c. Or if there's stuff, the integral of 1 over 1 plus stuff squared d stuff would be tan inverse of stuff. plus c. I'm going to do these pretty similar to how we did the sine inverse ones. Okay, number one. Let's do the integral of 5 over 1 plus 81x squared dx. Now, if these were just mixed up on the AP or something like that, it might be a little harder to pick these ones out than the sine inverse ones. This just looks like, I mean, if I hadn't told you anything before today, you would definitely just think of this as probably regular u sub. I would say always try regular u sub first, because 9 times out of 10, it's not going to be one of these new types. So always try normal u sub first. What I mean by normal u sub is when you look at a fraction, a lot of times that has ln involved. So maybe you would say let u equal the bottom, 1 plus 81x squared. What would be the problem with doing that? Well, right, when I take the derivative, du over dx, I'm going to get 162x. The problem with that isn't the 162, it's that x here that isn't part of the leftovers. So you'd get stuck. But again, 9 times out of 10, it's going to be a u sub like that, as opposed to one of these new ones. So if you're on the AP, if you try something that doesn't work, that's not a problem. What we are going to do and what is going to work is similar to what we did with sine inverse. We want this piece here to be what? U squared. Let u squared equal 81x squared. And it does kind of give you that tan inverse if you know to be on the lookout for it, because there's a 1 plus. That's kind of a key. This piece is a nice number squared, so that's kind of a key too. So u is going to be 9x. Now du over dx is just 9. We know when I take derivatives and I get constants, I don't have any issue. Dx is just du over 9. We can pull that out front. All right, so what is going to be out front? Not just 1/9, because I need to take this out too. So we're going to have the 5 over 9 out front times the integral of 1 over 1 plus 81x squared. Remember, that whole thing is u squared du. There's your tan inverse. So this is 5/9 times tan inverse of u. Don't forget your plus c when there's no bounds. And plug in c. 5/9 tan inverse of u, which was 9x, not 81x squared, plus c. All right, last example, and I am done. Let's do the integral. We'll do some bounds this time. From 0 to 1 of 1 over 9 plus 4x squared dx. Now again, if this was just in the middle of lots of different types of problems, I don't know if I'd think of tan inverse right away. It just doesn't get used that much. But if you tried regular u sub, letting u equal the whole denominator, you'll have an extra x. So no good. Now before I do u sub, what else needs to happen? Right, remember this needs to be a 1. So let's factor that 9 out. It's going to be the integral from 0 to 1 of 1 over, take a 9 out, and that leaves you with 1 plus 4x squared over 9 dx. So it's going to come out front. Right, it's going to be 1/9 this time, not 1/3, because there's no radical in the bottom. So I can just pull that 9 out, but it's in the denominator, so 1/9 times the integral from 0 to 1 of 1 over 1 plus 4x squared over 9 dx. Now we're ready for some u sub. What are we going to let u equal? Look, I need that bottom right spot of the fraction to be u squared. So let's say let u squared equal 4x squared over 9. So what's u? Take the square root, it's going to be 2x over 3. And remember, we also need new bounds here, and it's from the u that I do the new bounds. If I plug in a 0, well, 2 times 0 divided by 3 is obviously 0. If I plug in 1, I'm going to get 2/3. Okay, so du over dx is equal to 2/3. Really, I just want to solve for dx because that's my leftover piece. So that's going to equal what? 3/2 du. Okay, so now let's do our u sub. Out front, that 3/2 is going to be there. Also that 1/9 times the integral. We got new bounds from 0 to 2/3 of 1 over 1 plus u squared du. Kind of a lot going on here. What's 3/2 times 1/9? Well, you can think of that canceling with that. We're going to have 1/6. The integral is going to turn into tan inverse of u, evaluated from 0 to 2/3. Again, let's leave that 1/6 out front. We'll deal with that at the end. Okay, so we've got 1/6 times tan inverse of 2/3 minus tan inverse of 0. To try to evaluate, we're going to have 1/6 times, well, this is going to become, where's tan inverse? Again, we get rid of the left-hand side. It's positive, so it'd be in quadrant 1. Opposite would be 2, and adjacent would be 3. That's not a special triangle. So I don't really know what that angle is going to be. It's going to be an ugly number. We'd have to use our calculator for it. We could, but we don't need to. If we can't evaluate it, just leave it. How about tan inverse of 0? Where can tan be 0? Well, tangent is sine over cosine. Sine is y, cosine is x, so it's like y over x. We need that to be a 0 on top in order for the answer to be 0. So the only place where that's going to be true is this point right here. So this is going to become 0. 0 radians, but 0. So my final answer is just going to be 1/6. And I'm just going to leave it as tan inverse of 2/3 because it's just not a nice angle. When you're doing the homework and classwork, and usually it's going to come out to be a nice angle, but if it doesn't, just leave it as the inverse. Okay? All right. Problem set 113 is now officially assigned. And be aware if you're looking at answers on the answer key, which I hope you are, especially while you're not here to ask me questions readily. Be aware I have a note that the answer key has weird work. So don't copy down something from the answer key that you don't understand. If you have questions, as always, email me and we can set up a time to meet. All right, good luck.